Howdy, howdy. This is Mr. Potter. In our last episode, we started talking about integration by parts problem. And the idea was that if I take the antiderivative of f times dg, I'm going to get f times g minus the integral of g df. And the idea is that I'm going from a hard antiderivative to something that's easier. And we saw in our last example that we did that just because this antiderivative is easier, that doesn't mean it's going to be easy. Sometimes we'll have to do a use substitution. And sometimes we might have to do the integration by parts step again. So I want to go through a couple of examples where we're going to have to go through this procedure of integration by parts multiple times. So our first example is the antiderivative of x cubed e to the 2x dx. Now, we also mentioned in our last episode that I can use limit to help me determine my f. Remember that the closer I am to the front of limit, that's the more likely a function is going to be my f, and the closer I am to the end, that's the more likely that I'm going to be dealing with dg. And I notice here that I have a polynomial and an exponential. So I'm going to go ahead and let f be my polynomial term, x cubed, and my differential dg is going to be this e to the 2x dx. So f is x cubed. That means that df is going to end up being 3x squared dx. But when I take the antiderivative of this exponential, I have to use u substitution. U is going to be 2x, and I don't have a 2 dx. So I'm off by a factor of 2. So my g ends up being 1 half e to the 2x. And I notice that whenever I take the derivative of an exponential, the 2 gets multiplied. So whenever I'm taking the antiderivative, if this is a linear expression, then I could just divide by that coefficient. And so that's going to make doing this repeatedly, as we're going to have to do in this example, a little bit easier. So I've got the integral of x cubed e to the 2x dx. And this is supposed to be equal to f times g minus the integral of g times df. And so notice what I've got here. This is really x cubed times e to the 2x over 2 minus, and I can take this 1/2 and the 3 out, giving me 3 halves the integral of e to the 2x times x squared dx. And I end up with something that's easier, but it's easier only because the degree of my exponent has decreased 1 notch. And that's something that I'll notice when I'm doing integration by parts problems, is that every time that I do integration by parts, where it's a polynomial times a trig function or a polynomial times an exponential function, that I'll see my degree go down a notch every time that I have to take the antiderivative. So I'm going to have to take an antiderivative for x to the cubed, x squared, x to the first, and finally, when I have x to the 0, which is basically a constant coefficient. So we're going to have to do this several times, but that's okay. The procedure is exactly the same, because I still have a polynomial and an exponential. Lipid is still going to help me here. So for this problem here, f is my polynomial x squared, and dg is my exponential e to the 2x dx. And we've already figured out g because this is the same dg we had before. This is 1/2 e to the 2x. And my differential df is going to be the derivative of x squared, which is 2x. So what I've got here is my first term, which was the x cubed e to the 2x over 2 minus 3 halves of an integral. But this integral I'm going to have to evaluate. And it's going to come out to f times g minus the integral of g df. Let me clean this up a bit. So it's going to be the integral of g e to the 2x times df, 2x dx. And so all of this is going to be multiplied by this 3 halves expression. So what I've really got here is x cubed e to the 2x over 2 minus 3 halves x squared times 1/2 e to the 2x plus, because my negative times negative is going to give me a positive, this is really 3 halves times the integral of e to the 2x times x dx, because my 2 and my 1/2 will factor out. So I need to do this one more time. I need to go ahead and figure out what my f is going to be and what my dg is going to be. And I still have lipid helping me out here. So I know that f is going to be x, and dg is going to be e to the 2x dx. And so the antiderivative is still 1/2 e to the 2x, and the derivative of x df is just 1 dx. So for what I've got here, this integral that we've got is actually equal to x cubed e to the 2x over 2 minus, this is really 3/4 x squared e to the 2x plus, and I've got to do this 3/2 times this whole expression. So it's going to be 3/2 times f times g, 1/2 x e to the 2x minus the integral of g df. But this is just 1/2 e to the 2x dx. So when I distribute this out, I'm going to have 1/2 x cubed e to the 2x minus 3/4 x squared e to the 2x plus, and now I have to distribute this 3/2 across. So this is going to give me 3/4 x e to the 2x minus, this is going to be 3/2 times this 1/2, or another 3/4 times the integral of e to the 2x dx. Now we've done this integral 3 times in this problem. It's pretty obvious what the integral is, because we've done it so many times. So this is going to be equal to 1/2 x cubed e to the 2x minus 3/4 x squared e to the 2x plus 3/4 x e to the 2x minus 3/4 times 1/2 is 3/8 e to the 2x plus a constant. So to evaluate this antiderivative, I actually had to go through this procedure 4 times. And I know that it's tedious, but the process is exactly the same. I had lipid available to help me determine what my f and my dg was at every step of the process. So I was good with that. And the nice thing about having dg be this exponential is as the degree of f decreased, dg stayed exactly the same. And so this part was the same once, twice, 3 times, and we actually used it a 4th time to get from here to here. So it may be necessary to do integration by parts multiple times, especially if you have a large polynomial times a trig function, or a large degree polynomial times a exponential function. But just realize that every time you do it, you're going to decrease the degree by 1. And there are some techniques for doing integration by parts quickly in these situations, which we'll talk about in a later video. But I wanted to do one more example, and this is an example that comes up quite a bit, is dealing with these situations where I have exponentials and trigonometrics together. And I really do have to treat these a special way, and we're going to talk about how to do that right now. Again, Lipid is my friend because it helps me determine what f and dg are. And in this case, I'm going to want to let my exponential be f, and I want to let my trigonometric be my dg. So for our problem, f is going to be e to the 3x, and dg is going to be sine 2x dx. Now, I'm going to have to take the derivative of f, and of course when I take the derivative of something that has a linear term, the chain rule is going to give me just the derivative of that linear term, 3e to the 3x dx. Similarly, if I want to work backwards, I'm not going to be multiplying by this 2 because of the chain rule. I'm going to be dividing by 2. So this ends up being 1/2 times negative cosine 2x for the antiderivative of sine. And so the integral of e to the 3x sine 2x dx is equal to f times g minus the integral of g times df. And I notice that I'm going to have to do this again. Luckily, I still have Lipid to help me out. I'm still going to have that exponential and trigonometric. I've got negative 1/2 e to the 3x cosine 2x. Negative times negative is positive. I've got 1/2 times 3, so this is going to be 3/2 times the integral of e to the 3x cosine 2x dx. And I'm going to have to do this again. So I'm going to do this in a different color. So I'm going to have f is going to be my exponential, and dg is my trigonometric function, cosine 2x dx. So the derivative of e to the 3x df is going to be 3e to the 3x. And my antiderivative of cosine is sine. So g is going to be 1/2 sine of 2x. And so this problem becomes the integral of e to the 3x times the sine of 2x dx equals negative 1/2 e to the 3x cosine 2x plus, this is going to be 3/2 times an expression, 3/2 times f times g, 1/2 e to the 3x sine 2x minus the integral of g df, 3/2 e to the 3x sine 2x dx. And this brings an interesting point here. The idea is that my integral of e to the 3x times sine 2x dx is equal to negative 1/2 e to the 3x cosine 2x plus 3/2 times 1/2 is 3/4 e to the 3x sine 2x minus 3/2 times 3/2 is 9/4 times the integral of e to the 3x sine 2x dx. And I'm getting this strange feeling of deja vu because this looks exactly the same as this. And this illustrates one of the problems we have when we have mixed trigonometric and exponential functions. If we're trying to find the antiderivative of a product of a trig function and an exponential function, we'll end up in this never-ending cycle. And the reason we do is because e to the 3x doesn't actually simplify when I take its derivative. It just stays e to the 3x times a constant, e to the 3x times a constant, e to the 3x times a constant. And sine and cosine both alternate back and forth. First I'm sine, then I'm cosine, then I'm negative sine, then I'm negative cosine. As I take these derivatives, well, the antiderivatives work exactly the same way. So what I have to do is I actually have to move this over to the other side. I need to combine these like terms. Really, I have 4/4 of these. And if I add them to the 9/4 by bringing them over, I'm actually going to have 13/4 of this integral, e to the 3x sine 2x dx, which is going to be equal to negative 1/2 e to the 3x cosine 2x plus 3/4 e to the 3x sine 2x. And because that's true, I can really get rid of this coefficient by multiplying the reciprocal over here. And so I end up with my integral of e to the 3x times sine 2x dx being equal to 4/13 of this quantity here. So 4/13 of this negative 1/2 e to the 3x cosine 2x plus 3/4 e to the 3x sine 2x plus a constant. So whenever I have these trigonometric and exponential functions together inside of an integral, I'm going to have to do this cycle until I notice that I've got a repeat. And once I've got a repeat, I actually want to solve for this integral, because the ultimate question is, what is this integral equal to? Well, it's equal to 4/13 of this parentheses plus c. So this is the technique that we see whenever we have exponentials and trigonometrics together. It's not a pleasurable experience, but it's definitely something we need to be aware of. So this is Mr. Potter. Thank you for watching. Have a great day.